All right, so we are back in class, and welcome back, everybody. There's a few things that I wanted to talk about with regard to technology, interface, that type of idea before we get into class, and so we're going to do that right now. With regards to the test I did on Wednesday, the other class, the 10:30 class, I taught without using OBS, which is my video integrator. It allows me to transition easily between different feeds. I taught that without it, and then I taught your class with it, and there is a slight increase in lag due to the integrator, the software, but as long as I realize this and I wait for the tablet, which is probably the thing with the most obvious lag, then it seems to be okay. There doesn't seem to be too much of a problem in terms of the interface in that regard. So I'm going to continue using OBS to bring everything together. It allows this green screening and stuff like that. And we'll go from there. With regards to the material, last day, actually for both of the problem sets, I ended up asking you on the quiz what areas of the material were you struggling with. And so the key part of asking for feedback is closing the loop and coming back to you and telling you what the general observations were. Now, I present here what a lot of people would put down. So anytime that's like more than about 3 or 4 people made a comment, I would document it, and this is what I've got. Graphing, which formula to use, what is a reaction coordinate and how to deal with it. Those 3 are concepts that come with practice and working and helping with each other. And yeah, it's just a matter of getting comfortable with the course material. Significant digits, I can let you in on a little secret as to how I deal with it. Hayden McNeil actually can't determine how many significant digits you put in your answer. It can report the correct answer to the correct number of significant digits, but it doesn't have the ability to say, oh, this student, you submit an answer with too many significant digits. So the way that I go about doing it is Hayden McNeil will get the answer and say the answer is 48. But the real answer before rounding is 48.2. Hayden McNeil, I can set it up to say I will accept as an answer anything from about 48.0 to 48.4, so plus or minus 2, so 38.8 to 40. Let me try that again. Say the correct answer is 48.2. I can set up Hayden McNeil to take anything from about 47.8 to 48.2, give it a window such that it includes the correct answer. And that is what I do when I input the answers into the Hayden McNeil, so that even if you do put in an extra significant digit or 2, you will get the correct answer. Sorry about that. Rate determining step, same again. I didn't actually talk about rate determining step in class. It slipped my mind. It is the simple answer is it is the reaction that has the highest activation energy. That is the rate determining step. In the context of skipping steps and examples, yes, I do that on occasion, but what I skip is the basic algebra. I go through and endeavor to explain how the problem is set up. I set up the problem, make whatever simplification or approximations that are relevant, and then I take it to a point where it's algebraic manipulation. And in terms of doing lots of examples or doing fewer examples, I'm expecting you at this stage to be able to either in class follow the algebraic manipulation, or outside of class as you're rewriting your notes, go through and realize what algebraic steps I took to give you the final answer. In all of the examples I give the final answer at the end of the problem. If you don't understand how I went from here to there, like from steps where there's a bit of algebra to the final answer, there's lots of resources available to you. There's easily over 40 hours of teaching assistants, SIs, nucleus tutors available to you to assist you with that algebra. And I'll talk a bit about that in a bit. Finding the pre-exponential factor A, or the activation energy, again, often that is done through graphing, and that relates back up to what was said earlier in the context of practice. Hopefully will instill that and solidify that understanding in you. More examples. That's a balance. I've actually had people, didn't say on this one, but have said more theory. Other people have said more examples. And I try to balance that. I will give you a resource that has a lot more questions that you can do in terms of the problem set. And I will also give you the solutions guide to that. The solutions guide isn't a complete work solutions. It's the steps you need to take. And a couple people commented that they would prefer to see the steps, like what do I do next, what do I do next, what do I do next, and that's exactly what I'll be giving you, because I think that that's a better way to learn than here's the complete worked solutions. All right, so with that, I did want to go over here and look at these slides. So just give me a second here. I think that's going to do it. Right. So this, which will come up in just a second, this is a summary of the utilization of the teaching assistants for the week, for last week. And you can see that the TAs were used a lot on Sunday and Monday, and as we proceeded through the week, it petered off considerably. So that is last week. This current week is right here. And what we're seeing here is that there is considerably lower utilization of the teaching assistants, and of course we have still Friday to fit in here, but these people literally log in to collaborate. They sit in the course room and they're there to assist you with the course material. The TAs actually go through and do the problem sets. So they know how to do the problem set questions as well as the laboratory questions. And so you have them as a resource to go to. Utilize these people. You help each other out as well, but the TAs are there, and when you're sitting in the course room, you can help other students out, just like in the chat. Some people are answering each other's questions because I don't have the ability to do everything all at once. So I'm basically saying that the TAs and the SIs could easily see more students coming to them to offer their assistance on both the lecture and the laboratory portion of the course. Okay, that concludes the comments I wish to make on all of this material. Does anyone have any questions on that? Sorry, Benjamin, I don't know why. All right. The other thing I did want to mention to you is that as you mentioned, I'm new here, and so I'm a little behind in demonstrations, partially because I need to find things, and sometimes we don't have the chemicals available here at the university, and so things are being ordered and done. So we will slowly catch up with basically one demo a week, maybe 2 demos every 3 weeks, that type of idea. And so this one is a few days old. It should have been done earlier in the Equilibria unit. And what is, just to confirm, you can see my hand moving, right? This is obvious, you can see this? Yes? I'm going to assume that's a yes. I'll explain what's going on with this demo in a little bit, but what we have are 3 vials here, and each of these 3 vials contains the same chemical. It's a cobalt complex. And we're going to look, it's actually an equilibrium with two entities, which I will put up on the tablet in just a bit. What we are going to do is we're going to take them, and this is room temperature water. This is, of course, ice water. And the last one is going in, oh, that's hot, boiling water. And we will come back and look at them in just a few minutes as I go through and present the stuff that's going on. And where am I going to go with that? Off to the tablet. So, the chemistry that we have is we have cobalt, hexaaqua cobalt, reacting with chloride. That's an equilibrium. Sorry about that. With that. And now it's really slow. So that hexaaqua cobalt complex is, as presented here, red solution, and the tetrachloro cobalt complex is blue in color. And it is slowly catching up. Okay, if we now go back and look at the reaction, what we have quite obviously is that the room temperature one, water, hasn't changed. It's purple, which if you realize red and blue mixed together give you purple, this is a mixture of the two complexes. But in hot water, we have a very, very distinctive blue color. And in ice water, it is turning more and more reddish pink in color. So there we have the temperature effect. So what I would like you to do is go to this equilibrium and tell me which side does energy need to go on. Is energy a reactant or is energy a product in this reaction in order to explain the observable transition? I'll give you about a minute to think about it and type the answer into the chat, please. So we have many people who, in looking on this, are saying that energy is a reactant, which means that if energy is a reactant, then when we add energy, we're going to switch over to the right-hand side. And that is exactly what we observe. When we put this in hot water, we are adding energy and we are switching to a blue color. So yes, deduction is correct. Energy is a reactant. Good job. And what I'm just going to do right now is just go over and spend just so you can see what it looks like. Whoa, that's kind of cool. There it is. That is now after a few more minutes, and you get a very distinctive pink coloration for the cold water bath, and a very distinctive blue color for the hot water bath. And so illustrates principles of the temperature effects of the equilibrium constants. All right. What we are going to do now is just continue on with the course material. If I can find it. There it is. And just to remind you of what we did last day. Last day we did some examples towards the end, and we determined the solubility of silver chloride in pure water, and then in an aqueous solution containing some sodium chloride. That sodium chloride illustrates the concept of primary factors in Le Chatelier's principle, and we also were able to make an approximation that X is negligible, and that simplified the solution of this problem. In this example, we started only with the solid silver chloride, and so we were actually starting on the side favored by the equilibrium constant, so all worked exceptionally well. Similarly, for the solubility of magnesium phosphate, the challenge here was remembering how the stoichiometric coefficients affected the change line in your equilibrium and also the equilibrium constant. And so you worked through this and was able to calculate the solubility. And again, in this one, we started on the side favored by the equilibrium constant. And this second to last example that we did was significantly more complicated in that we had, to do a dilution of the different solutions to figure out what our initial concentrations were. And then we were not on the side favored by the equilibrium constant, so we had to shift over to products. Then we could assume that X was negligible, and we were able to solve the problem that way. Additionally, we made the assumption that all the cyanide was in the form of Cn minus, because cyanide is a weak base, and so at high pH, it is a reasonable assumption that it's all in the form of Cn minus, but it is a competing equilibrium that we need to take into account, or at least determine that it is negligible. That was the questions that we did last day. Now we're going to continue on by finishing off this chapter with this example here. And we have a solution now gaseous, a system that's now gaseous, and we want to determine the equilibrium pressures of each of the reagents presented here. All right. So I'm kind of hoping that I have a reasonable utilization, speed, that type of idea. So the equilibrium we have is that of carbon monoxide, not cobalt, plus chlorine is in equilibrium with phosgene, or COCl2. And the equilibrium constant for this reaction is 94 units of 1 over bar. What we don't have is the initial pressures. The equilibrium constant is in pressure, so we might as well calculate pressure in bar. So we need to go through and do that. What we have is 1 bar of gas, 1 mole of gas in 2.5 liters at 1200 Kelvin. And so using the ideal gas law, what we get is the pressure. And here, pressure is equal to, putting in all the units, 1 mole. The R value we need is the one that converts from bars and moles per liter, 0.08314 liters bar per mole Kelvin. The temperature was 1200 Kelvin, and this was in a volume of 2.5 liters. Looking at the units, moles cancel, liters cancel, kelvins cancel, and we have pressure in bar, which is what we would expect, which is great. You do the algebra, and you get 39.9 bar. So that is the initial pressures of carbon monoxide and chlorine. And you had 0 of the product, phosgene. The equilibrium constant still favors the products. It's greater than 1, but we don't have any products. So the first step is to shift to the side favored by the equilibrium constant, which means minus 39.9. And now we are on the side favored by the equilibrium constant. It's as far as we possibly can go to products. So now that we're on the side favored by the equilibrium constant, now we can go through and add x to set up and solve this problem. And if you were to have space, and conveniently I'm just going to delete this down here and it will work out for me, to illustrate the example of continuing the ice table. I literally am going to continue this ice table. That's my new initial conditions. Change and equilibrium. And given these initial conditions, it's now x and x minus x. You have that. And that is the equilibrium values that we need to substitute in such that we can solve this system and this problem. Good. So the equilibrium expression, K, is pressure of phosgene, pressure of carbon monoxide, pressure of chlorine. Substituting in values, you have 94, and I'm dropping the units, but you can work through and make sure the units all work out, is 39.9 minus x over x squared. That needs to be solved. Looking at the value for k, it's not extreme. If you tried to make the assumption that this was 39.9 over x squared, and where we assumed that x was negligible, what you would find out is that this is not valid and you actually can't do that. Nice try, it doesn't work because our equilibrium constant is not extreme. So that means we have to go back and solve this, the complete expression. This happens to be a quadratic. Yes, there's a quadratic formula, but I'm not limiting solutions to simple quadratics. You are going to be expected to solve any order of polynomial or any function. And in order to do that, you need to have technology available to you. So we are going to look at different, it's a V in there, different solver options. Now, if this was a normal face-to-face class, I would expect you to have a calculator that could do solver functionality because I would give you these things on an exam. So some calculators have this functionality. Okay, and there are websites that have this functionality. I'm familiar with Wolfram Alpha, and I believe in the last class another student put up another one. I can't remember what the name of it is, but it's actually in the chat further up. And so you have that functionality as well. But I fully expect you to either use a calculator or some website, needs an I in there, to solve these problems. To give you a hint as to how to set up and solve these things, it is infinitely better to get rid of anything in the denominator, to have everything on a single line. So that means we have 94x squared is equal to 39.9 minus x. Here you're never going to run into the problem, if x is really small, of the system crashing because it assumes that x is 0. So keeping everything on the numerator is important, and some require it to be equal to 0. Minus 39.9 plus x is equal to 0. Either one of those two you plug into solver will give you the answer that you need. In this case, it will tell you what the two roots of the polynomial are, and x belongs, try that again, x belongs to the set of 0.646 and negative 0.656. Those are the two values of x. The key part of this is the correct root gives all positive concentrations. The correct root gives all positive concentrations. And it doesn't matter if you have a third or fourth or fifth order polynomial, you're going to get 5 different values of x. Only one will give you all positive concentrations. So if I flip up to my ICE table that we have up here, we see that we have x over here. And so the only way that these concentrations are going to be positive is if x is a positive number. And so that's what we are going to end up doing. So the only root that works in this set is the one that is positive, 0.646. And each one of those numbers is one extra digit. So with that knowledge, we can say that the pressure of carbon monoxide at equilibrium is 0.65 bar. The pressure of chlorine is 0.65 bar. And the pressure of CoCl2 is 39.3 bar. All right. Now we did a lot of calculations here. If you want to check, just substitute it back into the equilibrium constant expression. And you're going to get 94.1, 1 over bar. So you didn't make a mistake in your calculations because this little quick check says that you get the right equilibrium constant out. What questions do you have on that? Afrin, sorry, I didn't realize you had raised your hand. My apologies.
That's okay. Could you go over again the difference between the two ice boxes that you made?
So we go up here, and our first ice table, let me just grab a color, that'll work. So the first ice table, which is this one right here, that shifted everything to the side favored by the equilibrium constant. Our equilibrium constant is greater than 1. And so this first ice table shifted everything over to the side favored by the equilibrium constant. The second ice table we have, which is this one right here with the heading. See, the headings stay the same, and I'm just following through. The second ice table is the second step in the solution, and here we introduce the idea of x to solve and actually get to the equilibrium concentrations. Does that answer your question, Efren?
So then why is it negative x?
Why is it negative x? Because if I look at what we've got here, I have 0, let me just get rid of some of these lines here. I have 0 for the reactant. So the reaction is going to need to proceed in this direction a little bit, right? So it means we're going to lose x on the product side and gain x on the reactant side.
Oh, okay, so it shifts.
It's shifting back a little bit. And if you look at the equilibrium values, it's not shifting back a lot. It's shifting back just a tiny, tiny bit. Okay?
Why does it shift a little bit?
Because we actually have an equilibrium. That x is 0.65. Because we actually need, at equilibrium, we have a little bit of each of the reactant and product. So there needs to be some of both in order to satisfy that equilibrium constant of 94.
Okay, got it. Thank you.
Not a problem. Are there other questions on this material? I'm liking using the tablet because I get to erase and I get to draw. This is good. I will continue to use that into the future. Other questions? All right. So what we have done is we've answered the question and done some examples. You now have the ability to complete all of problem set 3. We're just going to finish off this chapter and then I'll tell you when the quiz is going to run, if I haven't already told you. Teaching 2 classes does that to me. What are the limitations of ice tables? In the ideal world, we would know what's going on in the flask in our reacting vessel, and we would be able to take into account all of the possible equilibria that are occurring there. But we can't know what's going on in there. Often, much of the innovations in science are like, why did that happen? I don't understand why that happened, but that's interesting. That's how science advances, because we don't understand everything that's going on there. And the other one is it's computationally impossible in many cases to consider all of those equilibria. Leads us to a point that it is an approximation to assume that one equilibrium dominates through the reaction. And so this is just a series of examples of things that we often ignore. In the first, we often ignore the auto-ionization of the solvent. Liquid water associates to give you that, and that should be a liquid water, not aqueous water. When we look at the solubility of silver chloride, that's a very common example done in high school. It's a simple one to do. We don't realize or don't consider the fact that silver ions and chloride ions form a complex that's soluble, the silver dichloro-silver complex. And under normal conditions, that's a negligible reaction. But if you're working in something that has a high saline concentration, high salt concentration, where there's lots of chloride around, that second equilibrium becomes important and we can't ignore it anymore. And in addition, for example here, ammonia are weak bases, and so you're going to see complex ions formed and weak acids and bases that react in solution. We had that example, go back to it in a second, in the first one where we had to assume all of the cyanide was in the form of Cn minus, because otherwise cyanide is a weak base, and we set the conditions to give us cyanide in the form of Cn minus. So that concludes the chapter. In summary, equilibrium is a system containing some reactants and some products in a steady state. The forward reaction equals the reverse reaction. With the demo we did today, we saw that the equilibrium position is temperature dependent, and the equilibrium constant indicates the extent of reaction. The equilibrium constant ranges from 0, where the reaction doesn't proceed at all, it stays all as reactants. If it's less than 1, the reactants are favored. If it's greater than 1, the products are favored. And to a point where K is equal to infinity, where a reaction that goes to completion. Not a single reactant molecule remains for a reaction that goes to completion. We looked at solids and liquids, and we discussed briefly the idea of activity to say that that's why we can exclude solids and liquids from our equilibrium constant expressions. They have unit activity. They need to be present, but it doesn't matter. Once they are present, they're not going to affect the amount formed. We have Le Chatelier's principle, or the primary factors that affect equilibrium, as well as the secondary factors as well. Primary factors affect the entities present in the equilibrium expression. Secondary factors affect the environment that they are in. I reminded you of some of the types of equilibria: acid, base, solubility, formation, autoionization. It doesn't matter. They just happen to be named reactions. The method of solution for every single one of them is exactly the same. We need to start with the entities on the side favored by the equilibrium constant. That is, if K is greater than 1, we move all the way to products and then back up a tiny bit. If K is less than 1, reactants are favored. We move all the way to reactants, and then we move forward just a tiny bit using X to establish equilibrium there. And that is visualized by the figures in the bottom of this. But also, if your equilibrium constant is extreme, that is, if it's less than 10 to the minus 4 or greater than 10 to the plus 4, it may be possible to assume that X is negligible, which absolutely simplifies the calculations. But then if you are going to make that approximation, you need to go through and check to make sure that it is a valid approximation, and we are employing a 5% rule to do that. Questions? And while I'm here, did I tell you when your problem set 3 quiz was? I can't remember. Honestly, I can't. No? Okay, thank you. Are there any questions on chapter 15?
Hi, can you go back to slide 48? I just missed something.
Sure, I can go back to slide 48 and tell everybody. There we go. That one right there? This one?
No,
This one. Okay, yeah, sorry, my slide 49. Of course, I've added and subtracted things, so yeah. So your slide 48 is this one. So in terms of your quiz, it is actually next Thursday, Friday, and Saturday. So that gives you 6 days of material. The quiz is going to open on Thursday and will close Saturday midnight for you to do the quiz. I can say with that. And before anyone complains about reading week actually starts on Monday. I looked, I had to check. So, but you can still do the quiz on Thursday or Friday. But it will be open till Saturday at midnight. All right, any other questions on this material? I posted the YouTube video for Wednesday's lecture. I may have posted it yesterday because I forgot to post it on Wednesday. Sorry. Oh, I will look immediately after class. So I will look immediately after class to make sure I linked it to the playlist. All right. Well, if there are no other questions, we are going to continue looking at chapter 16, starting with chapter 16. So these are the concepts that we're going to be looking at in chapter 16. We're not doing section 16.7, but everything else in this chapter is going to be taught over the next couple of days. And of course, some of this material isn't taught in Chem 11-12. We're going to review it and take it to hopefully a little higher level. The problems are going to be a little bit more complicated, complex, pushing your understanding of this material to advance you along this path. To start with, we're going to look at just acids and bases in the real world. I'm not going to read this list to you. It's just presented to give you an idea of acids and bases are everywhere in the world around you. From the vitamins you might take to the food that you eat and drink contains acids and bases. Different compounds are used as antacids. Magnesium hydroxide, calcium carbonate are used as antacids for the stressful environments. But you use chemicals, acids, and bases in the world around you. One thing that is, if you look more into this, you will see that most foods are acidic. Fruit juices are acidic. Vitamins that you take are potentially neutral or acidic, but drugs and toxins are bases. Cocaine, snake venom, nerve agents often contain amines, nitrogen groups, and that makes them weakly basic compounds. If I were to look at the most hazardous chemical that you can buy, it fits one category: cleaners. Now, you as citizens in the world, if you know where to go, you can buy chemicals that are as concentrated as what we can buy here at the university. May not be the same purity, but you're still dealing with 98, 99% purity in the stuff that you buy. Excuse me. And cleaners are the things that are highly corrosive, toxic, aggressive chemicals. Why? Because if you think about what a cleaner has to do, you've contaminated something, you've damaged something, and you want it to be restored to its original condition as close as possible, fairly quickly. And the stuff that's on there is not something that simply brushes off. It is bound pretty strongly, whether it's an oven, an automobile engine, plumbing lines, that type of idea. You want something that's going to clean it reasonably quickly. So you're using very concentrated chemicals that are aggressively eating away at the residue or the problem. So cleaners, when you read the instructions on them, they say wear gloves, wear respiratory stuff, whatever, wear long sleeve clothes. Highly recommend you do that. And as a matter of fact, when you're done, put your clothes in the laundry, you take a shower, because often there's vapors that come out and that ultimately affect you, and you don't want them on your body as much. The other cute thing about chemicals is that the storage requirements that apply to us don't apply to you. You can put all of your cleaning agents and all of your chemicals underneath the sink or in the garage, and that's just where they go. For us, if someone were to come by and saw that in one of our storage rooms, we would be cited for unsafe storage of chemicals, because they are incompatible chemicals, and putting them together is just priming for an accident. And many household fires or damage starts from incompatible storage of chemicals. Just keeping you informed of the world around you, which is, one of the reasons why I want you to do projects. Let's find the chemicals in the world around you. In the last 5 minutes, I want to do a terminology review, and I'm kind of hoping that you can type the answers into the chat, and we'll go from there. So, can someone define for me strong acids or bases, and someone else define for me weak acids or bases? What is the defining feature of them, or the difference between strong and weak? Go for it. No, acids are, whether they're strong or weak, acids still have a proton. There we go. Yep, good. Christian says complete ionizing solution. Yes. Strong acids and bases completely dissociate or completely ionize in solution. Weak acids and bases reach equilibrium in solution. So you don't dissociate all of your weak acid or base. Good. What about the difference between monoprotic and polyprotic, whether it's acids or bases? What's the difference between monoprotic and polyprotic? You can talk too if you wish.
Don't monoprotic acids only have like one hydrogen rather than like two or three?
Haley, excellent. Yes. Monoprotic acids can donate only one proton. Monobasic bases can accept only one proton. Excuse me. Polyprotic acids can donate more than one proton. Polybasic bases can accept more than one proton. Good. That's using the Bronsted-Lowry definitions of acids and bases. How about amphoteric entities? What is an amphoteric entity? Anyone? A substance that can act as both an acid and a base. Excellent. Amphoteric entities act as an acid and a base. Can act as an acid and a base. So amphoteric entities can act as either an acid or a base. What about conjugate? How would you, in general, explain how conjugate entities differ? We might go 1 minute over here just because. I want to finish this slide. Conjugate entities. Anyone? Can you give me an example of a conjugate entity? One accepts and the other donates. What do they accept and what do they donate, Sarah? Or anyone? Hydrogen ion. Excellent. So, quite literally, conjugate entities differ through the exchange of a proton. That's all it is. Conjugate entities differ through the exchange of a proton. And Mark put up the example of acetic acid and the acetate ion, and all that differs is an H plus between the two. So conjugate entities differ through the exchange of a proton. So when we look at this next set, the stronger the acid or base, it's a one-word answer, the blank, the conjugate. The stronger the acid or base, the blank, the conjugate. Weaker. Good. Now the next one is slightly more challenging. What is the conjugate to a weak acid or base, and what is the conjugate to a strong acid or base? Just tell me what time it is. That's not helping. What's the conjugate to a weak acid or base? What's the conjugate to a strong acid or base? And yes, but no. The weak acid, stronger conjugate base. So that's probably the best answer. The conjugate to a weak acid or base is another weak base or acid. So the conjugate to a weak acid or base is another weak base or acid. And Mark's example of acetate, acetate is a weak base. Acetic acid is a weak acid. So if you have a weak acid, the conjugate is a weak base. The conjugate to a strong acid or base doesn't have any basic or acidic properties. So the conjugate to a strong acid or base doesn't have any basic or acidic properties. If you think about HCl, hydrochloric acid, the conjugate is the chloride ion. The chloride ion in solution doesn't spontaneously make a basic solution. It stays neutral. Sodium hydroxide. Sodium by itself in solution does not produce an acidic solution. So, well, the conjugate to a weak acid or base is another weak base or acid. The conjugate to a strong acid or base, it does not have any basic or acidic properties. And the final question here is, what is the reaction between an acid and a base called? It is neutralization. It's not actually redox. Redox requires a change in oxidation state. We'll get to that when we do electrochemistry. So the reaction between an acid and a base is called a neutralization reaction. Stuff that you should have had, hopefully this is a review material for you. That's going to conclude everything that we're going to do today. So I will stick around and answer any questions you have, but have a great weekend, and we will chat with everybody on Monday. Another demo on Monday, by the way.